Wave functions and atomic orbitals is going to be the topics of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in the last couple of lessons we've learned about the wave-particle duality of light, that light is both wave-like and particle-like in nature, but also about the same thing regarding matter with de Broglie's relation. So that matter, in addition to being particle-like, can also display wave-like characteristics. And then we saw Bohr's model of the atom. Now it was a quantized model, which is true, but the circular orbit's not quite right. In this lesson we're going to find out about orbitals and the wave functions that describe them. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now, as we pointed out in the last lesson, we give Niels Bohr a lot of credit for his quantized model of the atom. For it turns out that electron energies really are quantized. They only exist at certain discrete energies. Now, it turns out where he went wrong, though, is that he said the electrons live on circular orbits. And again, his model worked. At least it matched up with the math that corroborated the data for hydrogen's atomic line spectra. But it turns out that was pure coincidence because his model was wrong. The electrons don't actually live in circular orbits about the nucleus. They get further and further away, explaining why they're higher and higher energy. It turns out they live in orbitals, which are three-dimensional regions of space that are described by what we call a wave function. And this is related to the de Broglie relation, where, again, he kind of postulated that matter also has wave-like characteristics, and he was right, and we can see this with the behavior of electrons in an atom. All right, so these wave functions are complex mathematical expressions, and here's the simplest one. So it turns out this is the wave function for the simplest orbital, which is a 1s orbital. So it turns out these orbitals where electrons live, turns out we describe them as living in shells. There's a first shell, second shell, third shell, which we're going to see is also described as the K shell, the L shell, the M shell, and so on and so forth. And there's an infinite number of these shells. They just keep going higher. And the electrons get further and further away from the nucleus on average as you go to these higher shells, representing that they're also higher energy. Now, it turns out in the first shell, all you have is this single orbital, and it's a spherical shaped orbital, as described by this function where the variable is radius here. So you don't have to know these wave functions. I just wanted to give you an example of one here. But we use the Greek letter capital psi to represent wave function. But these wave functions, what they actually mean is still of a little bit of debate. They do have some utility. We start talking about bonding and things of this sort. But they don't actually tell you where the electron's going to be. And the reason they don't, and we can't use them to kind of represent the probability of where you might find an electron, is that they can have positive values or negative values depending on the region in space you're describing. And to say that something has a positive probability, no problem with that. If I have a 50% chance of winning the lottery tomorrow, you'd tell me to play. But there's no such thing as a negative probability. If I told you I had a negative 50% chance of winning the lottery, you just kind of scratch your head and be like, Chad doesn't know what he's talking about. There's no such thing as a negative probability. Can't have a lower probability than 0 for any event. And so what we do is we square these wave functions, and the wave function squared, that is what actually describes the probability of where you can find the electron. And sometimes you hear it called the probability function or the probability distribution function, same diff. And that is actually where these shapes come from. It turns out these shapes actually are described by both psi and psi squared, but when you square it, the shapes actually get a little bit bigger, but still resemble the same overall layout. The big difference is this, though. If you square positive 2, you get positive 4. If you square negative 2, you still get positive 4. And whereas the wave function itself can have both positive or negative values, the wave function squared is only ever going to be positive, and therefore, when normalized, can describe probabilities of where you can find an electron. And these are kind of the three-dimensional representations of the different wave functions. Now, one thing to note, these wave functions actually, again, as a function of radius, there's a finite probability that you can find them further and further away from the nucleus. But when you get past a certain distance, the likelihood of finding them at that distance becomes really, really low. But they never actually go all the way down to zero. The probabilities asymptotically approach zero typically. And so what we end up plotting are what we call the 95% probability distribution functions. So to a 95% probability, you'd find an electron within this sphere when it's occupying a 1s orbital. To a 95% probability, you'd find an electron in the 2p orbital somewhere within this plotted region. So, and again, there's a 5% chance you might find it further, but again, the further you go, the less and less it becomes. Now what you'll find though is that in the first shell, all there is a single s orbital. We'll find out in a little bit that orbitals can hold a maximum of 2 electrons. So, but I'm kind of getting ahead of myself. In the second shell, we'll find out there are both s orbitals and what we call p orbitals. And while the s orbitals are always spherical, the p orbitals are going to be dumbbell shaped like this. It turns out there are 3 of them per shell, and they lie on either the x-axis, the y-axis, or z-axis, so they're different in their orientation in space. Now in the third shell, in addition to an s orbital and 3 p orbitals, you're also going to get 5 what we call d orbitals. And these look like 4-leaf clovers, at least 4 out of the 5 do, with the 5th one kind of looking like this. Now the shapes aren't super important, but probably not the worst idea to be able to recognize an s orbital, a p orbital, or a d orbital by shape. All right, now keep one thing in mind here. So like for a p orbital, you will never find an electron at the nucleus, but you could find it on either side of the nucleus, either on the x-axis, y-axis, or z-axis, depending on which p orbital we're talking about. So these 2 lobes are part of a single orbital. That's not 2 orbitals, that's just one big orbital. Same thing here, there are 4 lobes in this d orbital right here, but it is one giant orbital, not 4 separate orbitals. Just want to make that clear. Okay, so now we've got these wave functions, which again kind of reflect that matter really does have some wave-like probabilities. And rather than looking at it as a particle that's going around in a circular orbit around the nucleus, it now has wave-like characteristics, and the wave function is spread out over some volume of space. Now, Heisenberg came along and made some contributions to this as well, and he came up with what he called his uncertainty principle. So ultimately, the Heisenberg uncertainty principle here is an equation, or at least can be described by an equation, where delta x here is the uncertainty in the position, and delta p here is the uncertainty in the momentum. And the product of these 2 uncertainties is always going to be at minimum equal to Planck's constant divided by 4 pi. So it's going to equal that or greater. And so what this means, though, is that when you're trying to look at where an electron is located, where its position is, you're going to have some problems determining where it is and kind of where it's going. Momentum, notice, is mass times velocity, and velocity is a vector described by how fast it's moving and in what direction. So you're going to have a hard time knowing exactly where it is and exactly where it's headed and how fast with infinite precision. And the better you might know where its location is, the less you're going to know where it's headed. The better you know where it's headed, the less you know where it is. So, and if you kind of think about this, let's say we have an atom here and we have an electron out here, and that electron is heading some direction at this particular point in time, and who knows exactly where. And we want to identify where that electron is. Well, the way you look at identifying where an electron is you shine a photon of light at it. So, and we have we can, there's a way to detect whether or not a photon of light has actually interacted with an electron. And so if I shine a photon of light, well, I can use a long wavelength of light, and then I'll know that it's somewhere kind of in this region if it actually interacts. Now, because I'm using a long wavelength, longer wavelengths have lower energy. So, and the way I'm going to know this actually interacted with the electron is that the electron actually absorbs the energy of the photon, but that changes its momentum. And so in this case, with a fairly long wavelength, it's not going to have a lot of energy, and so I'm not going to change the momentum of the electron in a significant way. Now the problem, though, is that with a long wavelength, there's a region of space where that electron might be found, and I don't have the greatest kind of exactitude of where that is. Now if I use a higher energy wavelength, and a higher energy wavelength is a smaller wavelength, now all of a sudden the region of space where I think I found this electron is a much smaller region. The problem is that when the electron absorbs the energy of that photon, it's going to change its momentum in a much greater fashion. And so I might now know the position of that electron better, but I know its momentum with less precision. Cool, that is the Heisenberg Uncertainty Principle. You could think of it as saying simply that you can't know the position and momentum of a particle, i.e. usually an electron, with infinite precision, and there's your limit right there. Now it turns out there's a version of the Heisenberg Uncertainty Principle that instead of looking at it as delta x and delta p, looks at it instead as delta E and delta T. So in which case, if you get a smaller and smaller time scale, then you can kind of notice some energy fluctuations for that electron. And the smaller the time scale, the greater the possible energy fluctuations you might see when trying to measure that energy of an electron. But as you lengthen out that time scale, as this gets larger, then the kind of the uncertainty and the energy can get smaller and smaller and smaller, again, within limits of this Heisenberg uncertainty principle. So now we're going to take a look at an orbital diagram here. And so every box on this diagram represents one of these lovely orbitals that exist in an atom. And so all these orbitals exist, whether they're occupied by electrons or not. And an orbital diagram is convenient because we get one box representing every one of these orbitals, and then we draw arrows inside them to represent kind of electrons that might be occupying those orbitals. All right, so as we go higher and higher up on these orbital diagrams, what we're doing is getting higher and higher energy. So if you look at the Schroedinger equation for the 1s orbital compared to the 2s orbital, what you'll find is that for the 2s orbital, when you solve for the average radius of that wave function, it comes out to be a higher number than for the 1s orbital. And being at, on average, a larger radius, that's a higher potential energy, similar to kind of what we saw with the radii for Bohr's model. And again, Bohr's model was wrong in circular orbits, but it did reflect something that was right, that as you go to higher and higher energy, you're on average further and further away from that positively charged nucleus. So in the first shell, which is sometimes called the K shell, we just have that single 1s orbital. So, and again, every orbital, it turns out, can hold 2 electrons, and we'll get there a little further in just a little bit. The second shell, so involves both s orbitals and p orbitals. Sometimes you'll hear this called the 2s subshell, and this is the 2p subshell. There's a single orbital in the 2s subshell. There are 3 orbitals in the 2p subshell. If you recall, the p orbitals were dumbbell shaped, and there's one on the x-axis, the y-axis, and the z-axis. So then your third shell, sometimes called the M shell, so has 3 different kinds of orbitals, 3 different subshells. The 3s subshell, the 3p subshell, and the 3d subshell. And notice where there's only a single s orbital, there are 3 p orbitals, and there are 5 d orbitals. Notice they're counting on the odd numbers, 1, 3, 5, for the number of orbitals in each of those subshells. And then notice we're going to have the 4th shell up here. It's sometimes called the N shell. This is not the last shell. There's an infinite number of shells, and you just keep kind of following the alphabet on your way up. What you should notice is this, though, is that you go to higher and higher shells, you get more types of orbitals, and we'll see why that is in a little bit. And so not only is there S, P, and D like there was in the 3rd shell, there's a new one, the F. Now it turns out you're probably not going to look at anything past F. There are orbitals that do exist past F, but none of the elements that kind of exist in their what we call the ground state, their lowest energy state, ever use any of the other additional types of orbitals, so we just never talk about them. Also, notice I didn't draw F orbitals up here. Well, one, because that's kind of the limits of where my artistic ability can go. They are complex 3-dimensional shapes that I definitely cannot draw. I can barely draw a d orbital, right? All right, so one other thing to note here is that if you look like within the L shell, I've got the s orbital and the p orbitals, and the p orbitals are slightly higher in energy than the s orbitals. And that's usually true, but not always. It turns out if an atom only has 1 electron, i.e. like hydrogen, well then it turns out all the orbitals within a given shell are going to be degenerate. They're going to be equal in energy. So for hydrogen, the s orbitals and the p orbitals would be all at the same level. They'd all be equal in energy, and we call that degenerate when they're equal energy. For hydrogen, the s orbitals, the p orbitals, and the d orbitals in that 3rd shell would all be equal in energy. So, all right, same thing for the 4s, 4p, 4d, 4f. They'd all be equal in energy for hydrogen. But once you have 2 electrons, that's when these different subshells split to different energies based on those electron repulsions. And so this is what you'll normally see. Now, when you're filling electrons in for an atom, if you want to know what orbitals are they occupying most of the time, so you start and fill in the lowest energy ones first and then work your way up. So that's described by what we call the Aufbau principle. And we're not going to go too crazy into how to fill the electrons in and stuff like that. If your course goes over it to a greater extent than we do, you might take a look at my general chemistry playlist in chapter 6 for a better, more detailed outlook on how to do electron configurations. Now remember that each of these boxes represents an orbital, and these orbitals, again, are just a three-dimensional representation of a wave function that is a solution to the Schroedinger equation. And it turns out when you start looking at the solutions to the Schroedinger equation, there's not just one solution, there are many solutions. So and it turns out when you start looking at these solutions, certain redundant numbers fall out that can lead to possible solutions. And we call these the quantum numbers. And they fall out as just kind of a general property when you're solving the Schroedinger equation. So, and we're going to kind of take a detailed look at what these quantum numbers are. So here are the four quantum numbers. We represent these quantum numbers with letters. And that might seem a little bit confusing, but you'll get a better idea of what a quantum number really is telling you here in a little bit. So, but the principal quantum number is n. So, and it's going to ultimately give you the shell number here. So the first shell, that means n equals 1. The second shell, where you got the 2s and the 2p orbitals, that's going to correspond to n equaling 2 for, again, some of those solutions in the Schroedinger equation. The third shell, the 3s, the 3p, the 3d, for all of those, n is going to equal 3. So, all right, so that's the principal quantum number. The next is what we call the orbital quantum number, or more commonly in a chemistry class, you probably hear it called the azimuthal quantum number. So, but this is going to tell you what kind of subshell, what kind of orbital are you in? An s orbital, a p orbital, a d orbital, an f orbital. So, and the way this one's going to work, so is that basically if you have a value of 0, that's going to correspond to s, a value of, that's still 0. It's supposed to say 1, a value of 1 for this orbital quantum number is going to correspond to p, a value of 2 is d, and a value of 3 is f. And so when you look in the different solutions to the Schroedinger equation, there are different possible values this value of L could take. And ultimately, it's going to tell you what kind of orbital you've got. All right, now the magnetic quantum number has something to do with kind of the orientation in space. And it turns out this can take on values from negative L to positive L. And when I say L, I mean the orbital quantum number. So depending on what orbital quantum number you have is going to determine what possible values this magnetic quantum number can take on as well. So if we take a look at this here, so if you recall, we said there are an infinite number of shells that are possible, which is why your principal quantum number can take on values from 1 all the way up to infinity. There's your range. So, and for the m sub L value, so the magnetic quantum number, it goes from negative L to positive L. And then we'll find out for L here, it can take on values from 0 up to, in this case, n minus 1. So if you look, for the first shell, n equals 1. And the only value of L that's possible, i.e. for an s orbital, is 0. Which is n minus 1. So we can take integer values from 0 all the way up to n minus 1, which in this case would be 0 all the way up to 0, which only includes 0. And that's why in the first shell, all we see is that one s orbital. Now, if you notice, if we go to the second shell, we see s's and p's. Well, for an s orbital, L takes on, again, the value of 0. For a p orbital, L takes on the value of 1. Well, because you're in the second shell, all of a sudden you can take on integer values from 0 up to 2 minus 1. So from 0 to 1, which includes both 0 and 1, describing s and p orbitals. So this is why we're going to get a new kind of orbital every time we go higher in shell number. So, because by the time we go to the third shell, you're up 0 to 3 minus 1. So 0, 1, and 2, s, p, and d in that third shell. So this is why we get a new kind of orbital each time. Now, if you take a look at the number of orbitals in each subshell, why is there just a single s orbital in the 1s, the 2s, the 3s, the 4s? Why is that? Well, if you look at the possible values for m sub L, it goes from negative L to positive L, and all the integer values yet again. So if L equals 0 for an s orbital, then it's going to go from negative 0 to positive 0. Well, then only integer that includes is 0, only a single value, which is why you only get a single orbital for the s subshells. Now, if you go to a p subshell, that's where L equals 1, which means that m sub L could go range from negative 1 to positive 1, all the integers in between, so negative 1, 0, and positive 1. 3 different values reflecting that there are 3 different wave functions that are solutions to the Schroedinger equation in that subshell. All right, so go to the d's, let's say. Notice there are 5 d orbitals. Well, that's because for d, L equals 2, which means your m sub L values could be negative 2, let's get this right, negative 2, negative 1, 0, positive 1, positive 2. 5 different values reflecting 5 different solutions to the Schroedinger equation, 5 different wave functions in that 3D subshell. And then finally for the 4Fs, notice there are 7 different orbitals. Again, they count on the odd numbers, 1, 3, 5, 7. So, and again, it just comes from the fact that F equals 3, or should I say L equals 3 for an F orbital. And so you get -3, -2, -1, 0, +1, +2, +3. 7 different values, again, describing 7 slightly different solutions to the Schroedinger equation in that F subshell. So that's kind of where this is constructed. So ultimately what you're getting here when you're getting these quantum numbers is you're in some way, shape, or form kind of getting an electron's address. Now there's one of these left, and we call this the spin quantum number. Now the spin quantum number actually isn't part of this solution to the Schroedinger equation. So these 3 actually fall out when you actually solve the Schroedinger equation and come up with the wave function, but this one does not. This is proposed later on by, I think, Pauli of the Pauli Exclusion Principle that we'll talk about in a little bit here. So, and basically he said that there seems to be some property of electrons, and he called it spin. So, and the exact historical nature of that, I'm not too sure, but it turns out it involves some sort of magnetic moment here. And you can kind of think of the way we usually think about this, and maybe this is kind of where it came from, is if you had an electron going around in maybe one of Bohr's circular orbits, so going around the nucleus. Well, if you did the right-hand rule, going around that way, so you could say, oh, it's negatively charged, and charged particles, when they move, result in magnetic fields. Now, if it were positively charged going around this way, your thumb would point in the direction of the magnetic field. Well, because it's a negative charge, it would actually point down. Well, it turns out then, what if you considered rotation exactly the opposite direction? And again, your right-hand rule, the magnetic field would point down if it were a positive charge, but up if it's a negative charge. And it turns out we do see these magnetic properties of electrons. And it turns out there's only 2 of these properties, and they're in opposite directions for their magnetic properties. So you can kind of think of it like charges. So charges, there are 2 types, positive and negative, and we can describe how they behave. Well, the spin, it turns out there's 2 types, and once again we can describe how they behave and their opposites. And it turns out we kind of refer to one as spin up and spin down, but it's kind of arbitrary. But again, the key is this. This is something that's an inherent property of the electron. It actually doesn't mean it's actually in one of these circular orbits. That might be related historically to kind of why they call it spin, but it actually is not related to any kind of revolutions about the nucleus or anything. It's some inherent property of an electron, just like charge is an inherent property of the electron. They're negatively charged. Just like mass is an inherent property of the electron. They weigh 9.11 times 10 to the minus 31 kilograms. Spin is also an inherent property of the electron and a lot of other parts of matter as well. Okay, so if we start filling electrons in, well, if you take a look at a hydrogen atom, hydrogen has just a single electron. And so you want to put it in the lowest energy place you can, so to be as stable as possible. And so for hydrogen, it just has that 1 electron. We represent it with an arrow. So, and sometimes we'll write electron configurations. And for hydrogen, we would just write 1s1. And the 1s refers to where the electrons live. And how many electrons live there? Just a single electron. And this is what we call the electron configuration. So the shorthand, if you will, or the notation we use to describe it. Now, if we move on to helium, so helium has 2 electrons. So, and in this case, where do we put the next electron? Well, if you recall, I kind of hinted to the fact that every orbital can hold a maximum of 2 electrons. Now, here's what Pauli ultimately said. He gave us his exclusion principle. And he said that no 2 electrons in an atom can have the same 4 quantum numbers. Well, I'm going to put another electron in this orbital right here, but you're going to note that I'm going to draw it with a down arrow instead of an up arrow. And it's the down and up arrows that we use to distinguish between these spin quantum numbers. Because these 2 electrons are both in a 1s orbital, for both of them n equals 1. So because it's an s orbital, for both of them L equals 0. When L equals 0, m sub L can only equal 0. And so since they can't have the same 4 quantum numbers, according to Pauli, one of them must have an m sub s value of +1/2 and the other one -1/2. And we kind of diagrammatically represent that with this up arrow and down arrow. So in this case, if we look at the electron configuration, we'd say this is 1s2. Now, if we move on to lithium, lithium's atomic number 3 and has 3 electrons. And so where do I put the next electron? Well, the 1s orbital here is full. The next highest energy orbital would be the 2s. And so in this case, we'd still write 1s2 and then 2s1 to describe that the 2s orbital has a single electron in it. So, and if we move on from lithium, atomic number 4 is beryllium, which has 4 electrons. So, and in this case, we'd add one more electron, and we do the opposite spin since it's going in the same orbital. And we now have 1s2, 2s2. Cool, and it kind of works its way up. The next electrons we'd stick would be in the 2p orbitals, and we'd start, putting some 2p with numbers and things of this sort. But this is really beyond the scope of what I want to cover in this physics portion. But again, if for any reason your professor covers electron configurations in greater detail, take a look at chapter 6 of my general chemistry playlist. I go into it a lot greater detail. We'll find out there are numerous exceptions and stuff like that that are typically covered in a chemistry class, but not necessarily in a physics class for how the electrons actually fill in. So a couple last things to say in summary. So you should know that we kind of fill orbital diagrams in from lower energy to higher energy. So real limited knowledge of how electron configurations work. So your quantum numbers, though, you're going to want to know what letters we use to represent them, the name of the quantum numbers, ultimately what they tell you, whether it's the shell, the subshell, the different orbitals within that subshell, or the spin up, spin down. And then the different ranges here. And then finally for L, so you're going to want to know that 0 corresponds to S, 1 to P, 2 to D, and 3 to F orbitals for that value. And one other thing, now that we've defined the quantum numbers, if you look here, you should see that in each one of the shells here, first the K shell is the first shell. Well, it turns out there are n squared orbitals in each shell. So notice the first shell where n equals 1, there's 1 orbital, and 1 squared equals 1. In the second shell where n equals 2, 2 squared is 4, and there are 1, 2, 3, 4 orbitals. So for the third shell where n equals 3, well, 3 squared is 9, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. The fourth shell would have 16 orbitals if you count them up, so on and so forth. And because every orbital can hold a maximum of 2 electrons, then it will be 2n squared as the maximum possible number of electrons in that shell if it's full. So in the first shell, that would be 2. In the second shell, notice you could fill in a total of 8 electrons. In the third shell, with 9 orbitals, that'd be a total of 18 electrons. And in the fourth shell, with 16 orbitals, you could hold a maximum of 32 electrons. If you have found this lesson helpful, consider giving it a like. Happy studying.